Hey, welcome back to the same lecture. Anyway, all right, let's draw one together to demonstrate what I'm talking about this expanded octet. All right, bromine trifluoride. Let's get back in the groove on how the heck to do this. Bromine is in group 17, so he's got 7 valence electrons. Fluorine, also a halogen, has 7 times 3 is 21, for a grand total of 28 valence electrons. We know that next we pick a central atom, so I'll put bromine in the middle because there's the least amount of him. And then we bond the remaining with sigmas, single bonds. We can call them sigmas now. So let's bond the extra fluorines. Make everything happy. Remember, 8's always the magic number, except for hydrogen, but that doesn't matter right now. So I'm going to add lone pairs to make everybody have an octet. Got it, thanks. Hooray, I put an octet everywhere. We want the magic number to be 28, so here we go. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. I think I did that wrong. Let me do that one more time. Stupid Friday. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. That went better. This is a new problem. We've never had this problem before. We're used to there being too many, right? And then we erase 4 dots and add 1 bond. We don't have enough. We need to add 2 more dots. Now, when this new problem happens, the question you're going to ask yourself is, can the central atom expand its octet? Can it break the octet rule? So the other way to ask that question is, does the central atom have an energy level of at least 3 or 4 or 5 or 6 or 7? Because then it can access empty d orbitals to break the rules I've taught you. Now, bromine does, right? Because bromine is hanging out. Oh, I'm not working today. All right, over here in 4p. So it does have an energy level of enough. So the answer is yes. We can expand bromine's octet. Are you ready? Mind-blowing moment. Here it comes. There's the 2 missing dots, and you're done. Expanded octet's actually easier than fixing the other problem that we previously did. We just teach it separately. But yeah, as long as the central atom can expand its octet, then you can do whatever you need to do to fix it using that central atom. And if you're asking yourself, well, what if he couldn't expand his octet? What if you needed 2 more dots and the answer was no? Well, then the answer would be that the compound that was given to you doesn't exist. So you don't have to worry about that even happening. All right, now I could actually straighten this up a little bit to make it look a bit more symmetrical. All right, this is a little bit, that would be prettier. But anyway. Yeah, yes, exactly. That's the whole point, is that bromine is now surrounded by 10 because it has broke the octet rule by expanding its octet by using empty d orbitals. But you're absolutely right. There's too many, but it's okay. Now, you can still assign shapes and angles. That sounds fun, right? But look at the regions of electron density. If I were to label them, I would say that it looks like this. I know it's pretty, right? How many regions of electron density are there? There's 5. You've never had 5 before, but I bet you could find a new shape in your packet. Go to the, it's still the last page, just the other side of it. Back to your shapes that we have dealt with quite a bit. And you will see that if there are 5 regions of electron density, that it is trigonal bipyramidal. Trigonal bipyramidal possesses multiple bond angles, and if you look, you'll see that the bond angles within that are both 120 degrees and 90 degrees, which I would say you better know, except for all of my assessments over this are open notes, so just know how to find it. What you think? Yep. So because the lone pairs can never like stack on top of each other. So I have a bond, that's 1, a bond, so now we're at 3. A lone pair will be its own, and the second lone pair will also be its own. It has to work like that. Yep. All right, let's draw some cards. Sulfur hexaiodide. Sulfur hexaiodide, yeah? All right, let's go talk to some people. Let's go over to cluster 4, seat 1. Hey, 4-1, how many valence electrons does sulfur have? 6 from group 16, very good. Let's go over to cluster 1, seat 5. Hey, 1-5, how many valence electrons does 6 iodines have? So iodine's in group 17, so how many does 1 have? It's in group 17. So it's got 7, all right? And then helpful, what's 7 times 6? 42. There's our magic number for a grand total. Ooh, this will be fun, right? Look at all these we get to draw. 48 valence electrons. I'm going to put sulfur in the middle because there's the least amount of him. And now we have this moment where, like Rutrow, it wants us to attach too many to the sulfur. So before you do it, ask yourself, can sulfur break the rule? Can sulfur expand as octet? What's the answer? As long as he has an energy level of 3, 4, 5, 6, or 7, the answer is yes. And sulfur absolutely can. So 1, 2, 3, 4, 5, 6. Ooh, I drew something weird. All right, here, look here. Stop writing because I need you to hear this. These weird shapes that I'm about to explain are not just because of expanded octet. These exist in all of the shapes that we've ever drawn together. It's another one of those things that we wait till we're outside the unit to show you. This is the simplest thing I'll go over today. A couple things. First off, you never have to draw them. All right, you'll never be asked to draw these two different types of shapes. The only thing I'll ever ask you to do is to take ones that I drew and tell me what they're saying, what they're showing. So you don't have to know where they go, when to do them, none of that. None of this is going to be difficult. But if you look back to your opening slide where you copied stuff down, you'll see that you drew a version of these, right? Mine are a little uglier. But here's why they exist in many Lewis structures. Us drawing on this whiteboard is not a representation of the real world because we don't live in a flat world, luckily. We live in this beautiful three-dimensional world. So if I were to take the sulfur hexaiodide off of the board and show it to you, it wouldn't just be going left, right, up, and down. Some of them would be coming at you, while some of the iodines off that sulfur could be going away from you. And that's what this shows. A darkened line like this is the boom, this is sticking towards you version of that exterior atom. Whereas this line shows that it's getting farther away. So it would be pointed towards the hallway on this whiteboard. Does that make sense? Again, that's all you have to know though, right? It's not when do I draw it, when does it show up? That's later in your chemistry life. But it's still a bond. Yeah, it's a sigma. It's a normal sigma bond. Right, so I could erase these and just draw the single lines. It would be the exact same thing. But to demonstrate this new vocab, coming towards you, going away from you, whatever, bonded to iodines. There's those 6 iodines. Make everything happy. All right, I'm going to shorthand it because I'm a terribly lazy teacher. But these are lone pairs that I'm adding. Unbonded is lone pairs. All right, now you can math this if you're smart enough to not have to count dots. So hopefully some of y'all have been mathing it. But to stick with the way I teach, here we go. Let's start right here, see if I don't mess this up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. So remember, these new funky things are just normal sigmas. Single bonds. Hey, we're done, yeah? No, I mean, we are. 48's the right number. Oh, okay. I mean, we're done drawing it, right? But there is a new shape. If you wanted to go back to Flower World, all right, that's 1, 2, 3, 4, 5, 6 regions of electron density. Drawing the flower is not a part of the chemistry, by the way. It's just me showing you what I'm thinking. Somebody yell out our new shape. It's octahedral with 90-degree angles. All right, well, let's see if you can do it. You try one, yeah? Astatine pentachloride. And don't draw darkened and dashed lines for the going away and coming towards you. Just be normal. Why don't you know, man? You're a chemistry pro. Astatine is AT.
Yeah.
If you get stuck, call me over.
Oh, yeah, you're right. Thank you. Thank you. Yeah.
No, it's both. It's 120 where the numbers are, and 90 where I won't ask how specific your question is, just both angles. Yes, you didn't have to do that. So, yeah. Oh, that's not right. How many zones are that's fine. Lone pair is the zone. Look back on our first example. The lone pair is the zone. Look at that flower. Yeah, and that's not it's 6. So be careful trying to use the formula to pick the shape, because this is misleading. If you've learned that trigonal bipyramidal, your new shape, has 5 regions of electron density, as it does, this looks like it's going to be trigonal bipyramidal before you do any work, right? It looks like it'll be this bonded to 5 things. But those of y'all that have done it have seen that something a little different actually happens. So do the work. Anyway, astatine is a halogen. Chlorine is a halogen, but there's 5 of them, so they're all in group 17. All right, so 42 valence electrons sound correct? All right, I'm going to put astatine in the middle. And then I'm like, ruh-roh, we need to bond too many things to him. Can astatine expand his octet? And the answer is yes. All right, and that has to be the answer, or I've given you a fake item that doesn't exist. So 1, 2, 3, 4, 5 things bonded to astatine. Here's my chlorines. Astatine has expanded his octet. Now I'm going to make everybody happy. So we'll draw our be good chemists and draw our lone pairs with dots. Don't want to always exude laziness. And now we have an octet everywhere except astatine, but that's his problem. Hopefully it's 42. What is it right now?
40.
It's 40. You can verify. All right. So we need 2 more. We already know that astatine is down to party. So give him the dots. Got to be a lone pair. I don't care where you put them, but it needs to be on astatine. And here's where our shape is misleading if you just use the formula, right? Because if we draw our fake non-chemistry flower to find our regions of electron density, you'll see that there are 6. Octahedral 90 degrees. Octahedral 90 degrees. No, we're not done. You'll look at I can't believe I finished this early. We're not done. There was one more vocab word on that opening slide, so glance at it with me, and we'll try to finish quickly. The idea of resonance is even easier than the idea of expanded octet, so this is no sweat. We've actually experienced the possibility for resonance before without me spending time on it. Here's what resonance is. Multiple ways to do this. Can you have a molecule that there's more than one correct way to draw it? And the times that we've run into this in the past is anytime you're doing the fix. Erase 4 dots, add 1 bond. You know how sometimes when we're erasing 4 dots, we always pull 2 from the central, but then when we're pulling the other 2, you have a choice on which exterior atom to steal them from, which is also the one you give the double bond to. That's where the resonance lives, because you could draw those molecules in multiple correct ways. So let's demonstrate it just so we can make sure we have it hammered down. Anybody know what ozone is? Oh, that's not the answer I wanted, but you're right. There's a layer of it around the Earth. Good at diffracting things that could harm us. It's also poisonous. If you consume ozone, it's no good for you. Which is funny because you're breathing in something that is almost identical to it. But ozone is O3, right? The oxygen you're breathing in with a little extra oxygen bonded to it. He showed up on your final exam, I think. Oh, it was on your homework. I knew it showed up. Oh, that's right. Anyway, let's do our VSEPR on ozone so I can show you resonance. Ozone, oxygen has 6 valence times 3 is 18. So 3 oxygen, so just stick one of them in the middle. Make everybody happy. Everybody needs 8. Can oxygen expand as octet? No, he can't. Oxygen has an energy of 2. There are no 2 Ds. So if we get in a situation right here, we're like, we need more dots, then turns out there's no such thing as ozone. And our whole life is a lie. But that's not going to happen. I just was asking a random question. Anyway, let's see if 18 is what we have. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. It's the old problem, all right? We have too many. So erase 4 dots, add 1 bond. Here we go. Erase 4 dots, 2 from the central. Y'all want to go left or right? All right. I heard left first. Erase 4 dots, add 1 bond. Now there's still an octet everywhere. 18 is the new number, and we're done. But here's my point. Here's what we're going to really look at. If we go and rewind 10 seconds, well, I'm going to redraw what we first had. We were there, and we were like, we need to erase 4 dots and add 1 bond. And I said, cool, so erase 4 dots, but we could have gone right. Erase 4 dots, add 1 bond. Ozone has 2 resonance structures because there's 2 different ways to draw it. So write down in your notes 2 resonance structures. I'm sorry? Nope. We're going to do another one. I'm just demonstrating that ozone does have resonance structures. Now, not everything does, and some things have many resonance structures. All right? But ozone has 2. There are 2 ways to draw O3, and there they are. Pretty simple, yeah? Let's do one more, and we'll call it a weekend. ASI3 plus 2, that looks fun. Ooh, nice. Let's get some help, though. Let's go over to cluster 3, seat 5. Hey, 3-5, how many valence electrons? Yeah, it's you, Donato. How many valence electrons does arsenic have? 5 is correct from group 15. All right, cool. Let's go over to cluster 4. C5, hey, 4-5. How many valence electrons do 3 iodines have? $21 is correct. 7 times 3. Now for the fun bonus question. Let's go over to cluster 6. Ooh, there's 5 of you in cluster 6. Seat 4, found you, AJ. It's 2 less, right? I didn't get to ask the question. Yeah, the positive 2 means it's positive, so we must be missing negatives. So this is ultimately going to say, well, make there be 2 less than what they're supposed to be. For a grand total of what? Yeah? Yeah. Central atom will be the arsenic. Because there's only one of them. Bond the 3 iodines to them. No, because it's floating around through space anyway. So in a moment, this gap, it will be on the bottom as it floats through. All right. Make everybody happy. Shorthand. If you're in the mood. Lone pair. If you're better than me. There's lone pairs. 24 is the target. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Erase 4 dots. Add 1 bond. Now stop. Look here. Look here. It says erase 4 dots. There's 1, 2. You could probably already see it. How many resonance structures does this model have? It's got 3, because there are 3 different ways we could go now. Right? I already erased 2. I could erase the next 2 over there, and that's one of the resonance structures. Or I could, have erased this one over here. There's the second resonance structure. Or I could have erased this dude. There's the third resonance structure. So make sure you have it in your notes that there are 3 resonance structures so that when you look back on Monday, you haven't forgotten all this. But this model has 3 resonance structures. Don't put your stuff away yet. There's something missing. What's missing? Why is my drawing still wrong? Yeah, right? Remember what ions get you? Don't forget them brackets. 2 plus, because that was his charge. And then let's ask one more question because I'm me. Cluster 3, smartest cluster in the room. C4, hey, 3-4. What shape is this? You can take a moment and look. It is trigonal what? Is it pyramidal? Planar. Yeah, remember, pyramidal has a lone pair on the central atom, and this stuff. So, make sure you're up to all this stuff. I'm going to give you another computer day on Monday, and then that quiz is Tuesday. I'm coming to see you.